Bayes' theorem is a very straightforward thing, which you've probably all seen before. So, but I am going to talk about it, but I'm going to talk a lot around it about misconceptions and issues that come up when you think about inference. So this lecture is going to be super theoretical, super conceptual. And of course, one of the things I love about data analysis is it has a lot of interesting conceptual and theoretical things underlying it. Please stop me if there's things you want to ask about. The whole point of this is class, and if you are confused about something, I'm sure there's other people in the room who are confused about it. And I'll repeat your questions onto the audio, although probably you have the little thingies if you are that good. Okay, I wanted to say, oh yeah, I'm going to emphasize something in what I say. I'm going to emphasize something about the likelihood function, and I'm going to sound like a crazy person. And that is partly because I am a crazy person when it comes to the likelihood function, but it's partly because LSST, the project, is making a big mistake, and it's on you to stop them. So this is going to be the Save the World lecture, where I'm going to tell you how you're going to save the world, and then you can either choose to accept that mission or not. Okay, here we go. Okay, so I'm going to talk about a situation where you have data, y. So think of it as y versus x. Maybe Adam even talked about fitting a line at some point. But your data y could be something pretty complicated. Like y could be the entire LSST point source catalog. Okay, so y is probably some pretty big object, or a stellar spectrum. A lot of what I work on is stellar spectra these days. Could be a stellar spectrum, or it could be the whole LSST catalog, or it could be the light curve of some time domain event that you are trying to understand. So this is a very general object. You could think of it as a vector. And if you did chi-squared and talked about chi-squared earlier, you probably did think of it as a vector. But this could be an arbitrary blob of data. Okay, so it's a very arbitrary object. I'm not going to put a vector hat on it because a vector hat implies that it has some metric structure, which it doesn't necessarily have. So this could be a collection of videos. It could be anything. Okay, and then your model is going to have parameters theta, and if you're measuring the expansion of the universe, these could be the mass density and the cosmological constant and the Hubble constant and so on. Or if you're studying a stellar spectrum, this could be like the temperature and the iron abundance and the magnesium abundance and so on. Okay, but again, I'm not going to put a vector hat on it because it could be an arbitrarily strange blob of things. It isn't necessarily a vector. And then I'm going to talk about the possibility that you also have nuisance parameters. And that's going to be important because nuisance parameters is a place where Bayes' theorem really matters. And nuisance parameters are generic. In fact, most data analysis we do have more nuisance parameters than parameters. So for instance, when you take an image of the sky, in principle, every pixel of your flat field and every pixel of your zero are parameters of your model, because you have to flat field your image and you have to dark subtract it and so on. Everything in there is a parameter. So you technically have millions of parameters, none of which you care about. You don't care what your CCD is doing unless you're studying CCDs, which some people in this room might study. But if you're not studying CCDs but are studying the properties of galaxies, for you these are nuisance parameters and you want to get rid of them. They're not your problem. So I'm going to give those a different name. Let's call them alpha. Again, this could be a blob of things, but this could in principle be very large. It's important to remember that your nuisance parameter set could be very large. And then there's going to be some ball of assumptions in your model. So there's going to be a set of assumptions, or you might call them choices, because your assumptions are the things you choose for your data analysis. And I'm just going to denote that by a capital I. It's like the information that you brought to the problem. And if you were doing least square fitting, these assumptions and choices are like the errors are the noise is Gaussian, and each data point gets its own independent noise, and all the things that Adam was probably criticizing earlier. Those are like your assumptions and choices. Okay, good. So that's my terminology. And let's just put this in parentheses for now. We're going to come back to that in a minute. We'll be there soon. But if I just take the other three things, there's various things I can write down. One thing, the most important thing I can possibly write down is, what do I expect for my data given the parameters? This is like the probability distribution. Actually, people have different names for this object, but the standard name for this object is the likelihood function. And this is given, if I make all my assumptions and I set my parameters, what are my expectations for the data? And this is written as a probability distribution. And I'm going to talk about what the properties that probability distributions have, because there's a lot of ways to make mistakes with probability distributions, and I want us to be very careful with them. This is the object, this probability distribution, which says if I knew my parameters, if I could set my parameters under these assumptions, if I set my parameters, what data can I get? What kinds of data can I get? Or what's the distribution over possible data? This is the fundamental object of inference. This is your job. When you're doing data analysis, your job is to write down this function or make an executable version of this function. And of course, later, hopefully, are you guys going to talk about likelihood free later in the week? Because there are situations where it's intractable to write down this likelihood function. One example that just comes off the top of my head is if you work on large-scale structure and you measure two-point clustering of galaxies, no one knows how to write down the likelihood function for the two-point clustering of galaxies. So the fundamental observable in large-scale structure, you can't actually write this likelihood function down, and you have to do something different. And people do a whole bunch of hacks to avoid this. But if you can possibly write this function down, this is your job. It's to write it down. And the interesting thing about that being your job is that that is independent of whether you're a Bayesian or a frequentist. Whether you're a Bayesian or a frequentist, you can take a frequentist approach to your data analysis, which is often a good idea, and I'll talk a little bit more later about why that can be a good idea. You still want to write down this object, because frequentist estimators also evolve from this object or derive from this object. This is the most important object in inference. And many people, when they talk about Bayes, they talk about priors and posteriors and MCMC sampling and so on, and you're going to go through all that over the next few days, but this is the object that is important. Why? Because this is the object that tells you how your data depend on the parameters. So this is the object that tells you what's the connection between the data and the things you care about. This is the thing. And there's a likelihood principle in Bayes. There's something called the likelihood principle, which I'm just going to write here, and you can look up on the internet, which is that all the information in your data about the parameters is encoded in the likelihood function. And another way, that's what a Bayesian would say. A frequentist would say your efficient estimators, your minimum variance asymptotically unbiased estimators are all maximum likelihood estimators. So the likelihood function is the thing that conveys the information about the parameters from your data. And so if you have data and you can construct this thing, you've now constructed everything anybody needs to learn about the parameters from your data. And actually, if you want an example of that, there's this Lambda archive. I don't know if anyone's used the Lambda archive, but NASA runs an archive called the Lambda archive, which is where the Planck data are kept and the WMAP data are kept. And what form are they kept in? They're kept in the form of an executable likelihood function, because that's how you interact with those data sets, is through the likelihood. That if you want to know about the cosmological parameters, if you're trying to combine Planck and WMAP data and some other piece of data, what do you need? You need the likelihood functions for those surveys. Okay, good. So the main thing, if you're only going to remember one thing from what I say today, the one thing I want you to remember is that your job is to write an executable likelihood function. I'm going to say other things which might be worth remembering, but that's the one I want. If I only get one, that's what I want. Years from now, when I run into you in a cafe and be like, do you remember anything from the lecture? You're going to be like, I remembered that the only point is to construct an executable likelihood function. Everything else can be done by others. Your job is to do this. And by the way, LSST's job is to do this. We're going to come back to that in a minute. Okay, good. And now, I'm going to talk about priors and posteriors and marginalization. I'm going to talk about a lot of different things. But first, let's write down some rules for probability distributions. So one of the strange things about the contemporary world is that you have multiple semesters of calculus under on your whatever transcripts, but you probably, most of you did not take a course on probability or measure theory. Everything in Bayesian inference straightforwardly falls from measure theory, because measure theory is the theory of probability distributions or of like how you do integrals. Basically, probability distributions are used to do integrals. We're going to see that in a moment. So I'm going to define the properties of probability distributions in terms of integrals, and then that's also a little bit of a guide for what you can and can't do when you're constructing and using these functions. Because if you obey the rules of probability of probabilities, if you obey the rules of the mathematics of probability, your inferences are safe, like are provably correct in a certain sense. So if I make these assumptions and I correctly construct this function and I obey the rules of probabilities, I get a correct inference at the end of the day. So that's why it's really important to know the rules of probability. So I'm going to be really, really boring about them. So I'm now going to talk about them really boringly, but they're critical because, and there are many mistakes out there, including by me in the literature. Okay, so partly because I was motivated by having made such mistakes, I wrote a little note on the archive, which is called probability calculus for inference, which is a little note. It's not that great, but it does have everything I'm about to say is in that note. So if you want to refer back to something, just look on the archive for probability calculus for inference. And it's just a very straightforwardly walks through the rules. It's not written that great. There's some confusing bits, but one day I'll update it, whatever. I also have something called fitting a model to data, which is 60 pages or 55 pages about fitting a straight line. So if you have trouble sleeping, this is a little bit less insane. Okay, now, what is the rules for probability distribution? I don't actually know all the rules. There's math is complicated, so I'm just going to say all we need to know for our purposes. If I have a probability distribution P of A given B, this thing has two properties, and if it satisfies these two properties with incredibly obscure exceptions, it is a probability distribution. The two things you need are that it's greater than equal to 0 for all A and B. This is probability of A given B is how you read this. You read this as probability of A given B. And this notation, by the way, is horrendous because I'm going to use the symbol P for all sorts of different things. So I'm overloading the letter P, which is ridiculous and bad. And people in the stats community use a better notation. But in astrophysics, this is the notation people use. So we're just going to go with it, even though there's much better notation in stats. So this is written as P of A given B. The idea is that if you tell me B, this is a probability distribution for A. So it's similar to up here. If you tell me the parameters, this is a probability distribution for the data. And that is one property this function needs to have. And the other property this function needs to have is that the integral of P of A given B dA is 1. And what is this integral over? It's over the whole possible domain of A. Now, why am I not writing limits on this? It's because, remember, these objects are complicated. They might be collections of videos or catalogs or something weird. So if this is a catalog, this is an integral over all possible catalogs, which is a pretty weird integral. So this could be a very strange kind of integral. If this is discrete, if A is discrete, this would be a sum. So if A is an integer, this would be a sum over the integers. Okay, there's different things, but so this notation is already pretty loose, you see, but if you sum in the appropriate way, it should sum to 1. Now, one of the things that you can conclude from this is that this object must have non-trivial units, right? Imagine this is a distance in miles, then this is in inverse miles, because when I do this integral, I have to get 1. So this thing has units of inverse A, which is a slightly strange thing. And the first thing I want to say is, if this is true and this is true, then that function is a probability distribution for our purposes. Good. And this is important. This looks very trivial, but it's very important because it relates to the point that probability distributions are used for doing integrals. They are measures. So if you're really a math nerd, there's like a metric and there's a measure. And the metric and measure are different things. And the measure is the thing that lets you do integrals. And this thing's a measure because it permits us to do integrals. And we're going to do integrals later. Well, we're not going to do any integrals, but I'm going to draw integrals on the board and we're going to talk about them. Okay, good. And then, of course, I like to, in the notes here, I like to write equations like this. That's not an operation you can do. You cannot do that operation. For one, it has really bizarre units. And for two, there's no reason that this integral would even be possible. Sometimes people are like, well, you could do that operation, but not necessarily, because they really live in different spaces. B could be in a completely different kind of space than this thing is defined. So it's not, you cannot do this operation. So it's very different for the variable to be on the left side of the vertical bar versus the right side of the vertical bar. That has a totally different meaning. And the idea is, this is not a probability for B. This is a probability for A once you set B. So it has nothing, it doesn't tell you anything about B. It only tells you about A. So not only is it say wrong, I'm going to cross it out. If I said you had to remember a second thing, that would be it, because that's a really big deal. I'm going to write one more integral, which is going to be useful for us, which is, if I have a probability distribution for two variables, like A and C given B, so now the idea is this is the probability, I could have said the probability of the joint object AC given B, meaning when I say P of A comma C given B, I mean the probability of A and C. So this is now in a bigger space. To integrate to 1, I'm going to have to integrate over both of these things to get to 1. So you can think of A and C as being one object now, is one way to think about it. There's different ways to think about it, but I want to do a particular integral on this. If I do an integral of this, dc, so I integrate over, actually, let's stay with A. I'm going to stay with my integral over A, because that's what the integrals I was doing before. If I integrate this, P of A given A and C given B, dA, then that will be P of C given B. And so up above, when the probability only depended on A, and I did the integral, I got 1. Here, when the probability depends on both A and C, and I do this integral, I get a probability for C, and you can think about that different ways. One of the ways you can think about it is units. This has units inverse A times inverse C. I did the integral dA. That kills the A units, but I've still got the inverse C units, so it must be an object with these units. Does that make sense? I actually think about units a lot when I do this. And well, actually yesterday, anyway, sometime last week, middle of last week, some collaborators and I realized we had a sign error in one of our papers, which was a little painful. And the way we worked it out was units. We were like looking back at an old equation, equation 11, and we're like, units aren't right. And so thinking about the units of your expressions is always useful. It's useful in all areas of physics. It's useful in data analysis. One of the funny things is when I wrote this point, that little piece up there, that you'll see, if you look at it, it's all about units, and it talks a lot about units. And then the stats community picked it up, and there was a little debate, some debate on the internet about it. And it really was clear from that discussion that no one in the stats community really thinks in terms of units. Thinking in terms of units in dimensional analysis is very much a physicist's thing, and a very useful thing. Okay, good. Questions to hear? Yes.
Does this relation depend on the relation between A and C?
Yeah, I mean, the question is, does this depend on the relationship between A and C? So this formula is correct no matter what happens. But if you were actually doing this integral, what would it look like? So imagine that A and C were very covariant objects. So imagine like this is the measure of the weights of panda bears, and this is the measure of the heights of panda bears. Then if you plotted those things, you would find it looks like this. Here's A, here's C. And so when you did this integral, when you do this integral dA, you're doing an integral like you're projecting the integral. I'm going to use all sorts of language that I'm used to because I've been thinking about this for like my entire career. But when you do the integral over A, it's like you're projecting the object down off the A axis, so you only have a distribution in C. And when you do that integral, you're going to get something here in the C direction that's kind of as big as this object. But if you think about what that integral looks like in detail, is as you're doing, as you're going in steps in dA, you're putting little bits of stuff here. And as you go to here, you're putting stuff across. And you go down. I don't know how you think about integrals, but I think of them like that you're stepping through, and at each step you're taking your stuff and you're putting it on that axis. And then you get a pile of sand like this. So in detail, what that integral looks like or how you do that integral depends strongly on what the shape is in this space. Does that answer your question, or is that relevant to your question? Does it work?
Oh, yeah. No, I was basically thinking if A and B are independent or dependent.
Good. Good. There's this word independent, which is thrown around, and it is used in these contexts. And independent is a very slippery word because independent means different things in different contexts. But here, A and B are not independent in the sense that if you know A, clearly you get a lot of information about C. Sorry, A and C are not independent here because if you know A, you get a lot of information about C. I prefer to use the word separable because separable is something that is more specific mathematically. So for instance, I don't know did you use a product of likelihoods over data points when you were fitting a line? Okay, fine. So sometimes, I'm going to do a little aside here because this is such a nice point. Sometimes if you have probability of y given theta. Imagine this is a list of measurements, and imagine you made those measurements independently, meaning imagine that this is the brightness of your star, and this is many measurements of the brightness of the star, and you think the star is constant in brightness, right? Then each of those measurements, if you made them with separate data, that didn't talk to each other, just independent pieces of data, then this probability will end up being a product over your n measurements of p of the nth measurement given theta and I. And that's the statement that, so this is what I would say is separable. Then your data are separable. You can treat each data point independently and just product them together. And that was not true here, because here knowing A tells you something about C. Here knowing one data point doesn't tell you anything about the other data points because they all are independently multiplying together. Good, that's a nice distinction. Now, that still may not relate to you. You're good? You're good, okay, good. Okay, good. Okay, good. So let's talk, I mentioned nuisance parameters up there. So there's, now we're going to let's start to get a little LSST-ocentric. So let's talk about LSST a little bit. So imagine you're using LSST to measure the cosmological parameters. So you're either, you could be doing various things. You could be doing a weak lensing map. You could be doing supernova as a function of redshift, or you could be doing large-scale structure. There's lots of different things you could be doing. So in that context, there are a set of parameters. So you might say that theta is your cosmological parameters. Of course, you could be working on the temperatures of stars or the metallicities of stars, or you could be doing all sorts of things as well. But let's just use this as an example. Theta is the cosmological parameters, and these cosmological parameters include things like omega baryons, omega dark matter, omega lambda, H naught, sigma 8, and so on, various parameters. And then what I'm going to think of as our nuisance parameters for now are things that are like calibration parameters for LSST. So as I mentioned, things like the flat fields, the photometric band passes, the atmospheric transparency, all sorts of things about like how the survey operated. So these are going to be like survey calibration. And let's imagine that you are a cosmologist, not a hardware person. Of course, there are hardware people who might use the cosmological experiment to understand the survey calibration parameters. And that sounds absurd, but that's what I did in Sloan Digital Sky Survey. When I worked on Sloan Digital Sky Survey, we used the properties of stars to figure out what the detector was doing. And for us, we were marginalizing out the stars to learn about the detector. Here, in the more normal setting, is you're marginalizing out the instrument to learn the cosmological parameters. There's another concept of nuisance parameters that also comes up, which is you might only care about resolving the H naught controversy. You might not care about the matter densities. So you might consider these and sigma 8 and so on all as nuisance parameters as well. So there's two kinds of settings for nuisance parameters, but I want to distinguish those two because there's a big technical difference between those two sets of nuisance parameters. Because these are nuisance parameters that other experiments care about, whereas these are nuisance parameters that nobody else cares about. You can't do an experiment with Sloan Digital Sky Survey hardware and learn about the LSST calibration. Whereas you can do an experiment with Sloan Digital Sky Survey that tells you about these parameters. You see the distinction I'm making? So there's nuisance parameters and there's nuisance parameters. These are nuisance parameters because these are the ones where nobody cares. Except, of course, the people building LSST. And furthermore, if your knowledge, say you're working on LSST, say you're building a subcomponent of LSST, then your knowledge about these parameters is the best knowledge about those parameters in the world. Whereas no one in the world can claim that their knowledge of the cosmological densities is the best in the world, because lots of people are contributing to our knowledge about these. In fact, famously, you have to combine supernova data and large-scale structure data in to constrain these parameters well, and weak lensing and CMB and so on. So famously, you have to combine multiple experiments to get these, whereas these live only inside your survey. Do you see that distinction I'm making? That is a relatively important distinction for what's about to happen. And it relates very much to the mission I'm going to give you to save the world. Okay, good. I'm going to take a little aside and talk about a graphical model for a second. Are graphical models coming up later, do you think? Good. Excellent, good. So I'm going to flash you a graphical model, which you're going to understand later. Good. The probability expressions can be represented graphically. And that's an incredibly useful tool. And it's a very useful tool for a number of reasons. One is that it is very good for communicating with people, very good for communicating your model assumptions. So if you have a model of data and somebody else has a model of data and you're trying to understand how your models relate, if you both draw your graphical models, it's a way to compare your assumptions. So graphical models are a very useful way of describing what you're doing. It's also a very good way to communicate to the computer science literature and to the math literature. So if you're talking to a mathematician and they're saying, what are you doing exactly? And you start going on about stars and galaxies, their just eyes glaze over. But if you draw your graphical model, they're like, oh, that's interesting. What functions are using in here or whatever. They can engage with you better with these graphical models. So this likelihood function is part of a graphical model, or it's a piece of a model that looks like this. I make my assumptions. I have assumptions, those fundamental assumptions. Those fundamental assumptions lead to a parameterization of the world. And those parameters produce the data, and the data are observed. So these are some fixed assumptions that I made up front that I'm not willing to change. Those are my decisions. Within those assumptions, there's a set of movable parameters which I would like to infer. And those parameters generate the data. And this graphical model leads to a expression. If I wanted to write down the probability for everything in here, P of theta and y given I would write it as P of theta given I, P of y given theta and I. So actually I can even simplify further. This graphical model leads to that expression. This is the thing which would be called the prior, and this is the thing that would be called the likelihood function. It's the probability of the data given the parameters. The prior is the probability of the parameters before you've seen any data, and this thing is called the joint, which is what you're allowed to smoke in a small number of states. And this, what does this model mean? What does this graphical model mean? The way this is drawn has something to do with how I wrote these down. And when you learn about graphical models, you're going to learn about what's the relationship between this graph and this expression. And different people have slightly different conventions there, so they might not even draw it exactly the same way. Yes? Good. Technically, I think you could put the I here. I like putting the I here because it reminds you that this involves assumptions. And then my graphical model becomes this. And it says my assumptions affect my parameters and affect my data. So technically what I wrote up above, let me rewrite it like this, then it's this graphical model. And the graphical model has arrows because the graphical model also has a kind of causal interpretation. Like I make assumptions, and under those assumptions, these are the fundamental parameters, and those parameters create my data. So you can think of it also causally as like a direction of causation. Though if you're a really hardcore physicist, you don't believe that causation exists. But anyway, that's for coffee time. Okay, good. Now, if I have nuisance parameters, alpha, my graphical model gets a little more complicated. Because if I have nuisance parameters, I have my fundamental assumptions, and my fundamental assumptions produce my parameters. But also there's nuisance parameters, and these two things produce my data, which is observed. And I guess technically, since we're carrying through, I should do that. So this is going to be our new graphical model, that there aren't just parameters, there's also nuisance parameters, and both the parameters and the nuisance parameters create my data. And notice how, because I'm calling these calibration parameters, I'm thinking of the data as being fairly raw. You see, I'm thinking of it as kind of raw data because the data are being affected by both my fundamental parameters and my calibration parameters. So you could think of this as like raw magnitudes of type 1a supernovae, like instrumental magnitudes. And the instrumental magnitudes I get are partly because different supernovae are at different places in the Hubble flow, and partly because on different nights the transparency was different. And both of those things matter to the instrumental magnitudes that I saw. That's kind of the thing I have in mind. Okay, good. So let's talk a little bit about that. Actually, yeah, I want to keep that board up. So I'm going to erase the likelihood principle, which is the only thing I need you to remember. One of the interesting things about what I'm telling you, how are we doing? Oh, we're doing okay. One of the things you might notice about what I'm telling you is I haven't mentioned the posterior probability yet. And you might think, well, this is electron Bayes, so it should be about there's a prior and there's a likelihood and a posterior. Why haven't I mentioned the posterior yet? It's because I don't think we should construct posteriors. That's not something we should be doing. And that relates to the mission I'm going to give you at the end of this. Okay, but I will tell you what the posterior probability is in a second. I need to, because A, I've been assigned to tell you what it is, and B, you have to be able to read the literature of wrong papers. Okay, good. Now, this is my new graphical model. So I'm now going to write down the probability factorization in that graphical model. It looks like this, that the probability of theta and alpha and y, all the things in the circles, theta, alpha, and y is the thing you observed, theta and alpha are the things you want to know about. The probability of all three, given the assumptions, is the probability of theta given the assumptions, the probability of alpha given the assumptions, and the probability of y, the data, given the parameters, the nuisance parameters, and the assumptions. That is the factorization of probability for that graphical model. Good. How's everybody doing? Now, imagine there's all sorts of projects measuring the cosmological parameters. There's supernova projects measuring the cosmological parameters. There's CMB stage 4 projects measuring the cosmological parameters. There's the Euclid mission is measuring the cosmological parameters. And here you are in LSST, and you've done your supernova project, and you've measured the cosmological parameters. So everybody's measuring the cosmological parameters. And you want to write the consensus paper. You want to say, if I combine all this information we have about the cosmological parameters, what's the answer? What do we get for the cosmological parameters? Well, how do you combine data? How do you combine data? We're going to come back to this expression. I've written this expression. It's just sitting here. We're going to come back to it in a minute. We're not there yet. You can see, many of you can see in advance, this is going to turn into a posterior and marginalized likelihood, and various things are going to appear out of this. We'll come back to that in a second. How do I combine data sets? Well, what you do is you say the probability of all the data, like there's the data you got from LSST, and there's the data you got from whatever. Let's say Simon's Observatory, since we're here locally. So imagine I'm trying to combine LSST and Simon's Observatory. I want the likelihood function. What's the likelihood function for all of these data given the cosmological parameters and our assumptions? And technically, there's going to be two sets of assumptions here, right? But I'm just going to combine them into one. Let's imagine these are all the assumptions of all the astronomers in the entire world. Okay? This likelihood function for both the LSST and the Simon's Observatory data, well, these data were taken by the Simon's Observatory in one site. These were taken by LSST in another site. These two data sets are independent. They are separable. So I can write this as a probability for the LSST data, given the cosmological parameters, times a probability for the Simon's Observatory data, given the cosmological parameters. So as long as the Simon's Observatory can give me this likelihood function, and you guys can give me this likelihood function, I'm good. The problem is, look at this. The likelihood function you just wrote down depends not just on theta, but also on this alpha that I don't care about. And notice, imagine the Simon's Observatory. You can think about it. It will also have its set of nuisance parameters. You see, both surveys will have a set of nuisance parameters that I don't want to deal with. Because I don't want to infer this. I don't want to make a commitment about those nuisance parameters. I don't want to infer those nuisance parameters. I just want them to not be there. I just want to do this multiply. So can I do this multiply? It turns out yes, provided that these two surveys are sufficiently Bayesian. And this is the location where Bayes finally enters. Bayes enters because I need to get rid of these nuisance parameters from this expression. So I have a likelihood, P of y, given theta, alpha, and I. But what I want is P of y given theta and I. That's what I want. That's what I have. So what I want to do is this. Don't write this down. Why are you not allowed to write that down? It's wrong. It's the product of W, R, O, N, and G. I'm glad somebody thought that was funny. I'm just surprised it was Lucy Ann. So you're not allowed to do that integral because it has the wrong units. So I have to do something here to get this into the right units. And what you do is you use the prior on alpha. That will get me into the right units. You see, if I multiply P of alpha given I, d alpha, see how this now has the right units that I'm allowed to do that integral? And that will give, how many times do you think I can do that? That will give me the likelihood that I want. Now, many things to say about this. First of all, this Bayes just appeared. Bayes hasn't really appeared up till now. The only sense in which I've been Bayesian up till now is I said there's this likelihood principle that all information flows from your data through this likelihood function. But here, Bayes appears because in order to get rid of this, I needed to have a prior on it and do the integral with that prior. And only a Bayesian can do that. A frequentist cannot do this operation because a frequentist does not have a prior on the parameters. So mathematically, a frequentist cannot do integrals, which is, actually, it's very hard to live your life as a frequentist. So if anybody wants to live their life as a frequentist, it's like deciding to be a Buddhist monk. Like there's only certain things you can do if you are a frequentist. For instance, you can't say, oh, the cosmological parameters are these. You can say, the data are consistent with cosmological parameters in this range. And you can't do any integrals in the parameter space. And it comes from a fundamental view in frequentism. The frequentist position is very good. It's a beautiful position, actually. The frequentist position is that it's an unnecessary assumption that it's possible to write down a measure in the parameter space. After all, it's God's responsibility to put down a measure in the parameter space. All we do is construct experiments. And this is saying that you know something about the relative probabilities of nuisance parameters, which by assumption you don't care about. So it is a strong assumption. So Bayesians are making a strong assumption that they have such a measure, but in exchange for that strong assumption, they get to do this integral. And since you get to do this integral, you can hand forward the marginalized likelihood that only depends on the cosmological parameters. And you can even put that in the lambda archive. Right? And the Simons Observatory can do the same kind of integral to get this, and then they can put their likelihood function in the lambda archive, and then we can all go to the lambda archive and combine the likelihoods and do inference using all the data. Okay, good. So a few comments to make. One is Bayesians can do integrals. That's one point. Another point is notice here that LSST is handing forward this likelihood function so that people can do inferences. Notice that LSST does not have to produce a posterior. They only need to produce a likelihood function. But I need them to marginalize out their nuisance parameters because I don't care about the nuisance parameters. Well, actually, I probably will care deeply about them. I'll probably end up being on the calibration team. But if I'm doing cosmological inference, I want this marginalized likelihood. I don't want your posterior beliefs about the cosmological parameters because I won't share your prior, and plus I want to include other information. I want your likelihood function. And you, as an LSST observer, you want Simons Observatory's likelihood function. You don't want their posterior probability because you won't have the same priors as them. Things will have moved on. Things will have changed. You'll believe different things than they believe. After all, they're CMB observers, and you're an optical observer. CMB observers and optical observers have totally different beliefs. And, well, not totally different, but very different. And so you are going to want their likelihood function. You're not going to want their posterior probability. You want their likelihood function because that's the thing you're going to combine when you make your inferences. Getting a sense of what mission I'm going to propose to you? Okay, good. Okay, so Bayesians can do integrals. And the second thing is it's important to have priors on your nuisances. You don't have to have priors on everything. A lot of Bayesian talk is about, oh, you have to have prior beliefs, and then you have to have a likelihood, and you multiply them together, and you renormalize, and it's called your posterior beliefs, and that's how Bayesianism works. But that's not true at all. You don't have to go fully to a posterior belief, but you do need to have priors on your nuisances, because your nuisances you're going to want to integrate out so that you can hand to your users something useful. And I've been talking like LSST, but this is true for every project you ever do. Even if you're just trying to get the parameters of a single exoplanet system based on a TESS light curve. again, the most important thing is that you produce a likelihood function and that you integrate out your nuisance parameters. The nuisance parameters that you know well, you need to have priors on them and integrate them out. Because that way you can pass on to the exoplanet community your likelihood function for the properties of that exoplanet, which can then be used by other observers when they're trying to figure out when they want to combine in their radial velocity data with your test light curve data. Okay, good. Sorry, my handwriting is so poor. Yes. Oh, nice. Use the mic.
When you say nuisance parameters, you mean the actual nuisance parameter, like purely nuisance parameters.
Good. I'm being very clear. I'm trying to be very clear here about this distinction between the cosmological parameters, which would be shared by all the different surveys, right? Both Simon's Observatory and LSST are inside the same universe. So they both share these cosmological parameters, all of them. And so in this context, what I mean by nuisance parameters are what I called the nuisance parameters, which are the ones that are really unique to LSST. So this was the LSST integral where I took out the LSST parameters. And there's another set of such parameters for Simon's Observatory, and a similar integral was done at Simon's Observatory to deliver me this. Is that the question you're asking? Good. Yeah.
Seems like from if you fix what your cosmological parameters are, that will define the likelihood. So say WMAP puts their lambda CDM likelihood on the lambda archive. But what I want to study is some extension. Does the likelihood that they put there not what I want then?
That is a great question. That is a really good question. One of the issues here is if I want to multiply these two things together, these two likelihood functions can be defined for many different values of these parameters, but the parameters here have to be the same as the parameters here. Otherwise, there's no point in multiplying these together. So one of the big issues, that's why, by the way, they both have the same I here, because they have to agree on certain things. So if this was all done in like steady state cosmology, and this one's done in lambda CDM, there's no point in multiplying them together because they have different parameterizations and they don't connect to the same things. So it is still the case that the community has to make certain kinds of overall decisions about what parameters we're going to work in. And one of the things that's been so fortunate for us about the cosmological model being so simple is we do actually agree on those parameters. But if you're working on crazy extensions, like if you're working on, some theory that involves primordial black holes, you will not be able to, you will have to rewrite this likelihood function and this likelihood function, and you're going to have to go back to Simon's Observatory and say, I need to redo this marginalization integral with a new likelihood function. And I think because the community is getting so sophisticated now, I think that the Simon's Observatory and LSST will be open to that. I think they'll say, okay, bring it on, but bring some computers. But that, in my ideal world, that's how it's going to work. If you want to extend the standard model to some weird direction, hopefully these projects will give you the tools to do that. And that's kind of a subpart of the mission I'm going to assign you. Other questions? Yeah. Blue light, green light, you're good.
So how if I am building an instrument, how do I write down the prior? And can I write down like a posterior of alpha given I and some calibration data?
Good, that's a great question. How do you write down this prior? Where does it come from? Where did this prior come from? How do you write it down? There's no general answer to that question, I'm afraid. But let me say a couple of things. One thing that's very important in Bayesian inference is that when your data are good, it doesn't matter what you write down here. So if your data are very informative about alpha, then it doesn't matter whether you put a broad prior or a narrow prior on alpha. If the data are very informative, you get the same answer here. And so the first thing to say is try to take your data such that it constrains your nuisance parameters, because then your prior on the nuisance parameters doesn't matter very much. And that's actually a lot of what I did in Sloan Digital Sky Survey. When I worked on Sloan Digital Sky Survey, the plan for the survey was it would take a single pass across the sky. and then shut down and throw out the camera. And we said, you know, if you take some cuts the opposite way, we'd learn a lot more about the parameters because instead of just having data going this way, we'd have some data going this way that would cut through all the other data. And we convinced the collaboration, they took the data, and then all of a sudden we really became very informative on these parameters, and then our prior on those parameters didn't matter in the end. So that's the first thing to say. The second thing to say is if you don't know much, if your data aren't very informative in some directions here, those will fundamentally be directions that you get wrong. They will be things you get wrong because in general, you never have very good priors. Like this might be something, if this is like the transparency of the atmosphere, you might have a lot of historical data on the transparency of the atmosphere and you could use that historical data. But in many cases, there'll be things you know nothing about. Like if you're doing a spectrograph, there's some wavelength solution. You really don't know what the prior is over the wavelength solutions in your spectrograph. Now in principle, sometimes you can look at other data from the same spectrograph and figure out what kind of distribution it has, but usually in practice, it's very hard to make good models for this. So it's best to take your data so that these are very well constrained, and then it doesn't really matter what you put in there. But I'm sorry, that's a very unsatisfying answer. How am I doing? I've just got a couple minutes. Good, I'm very close to done. Okay, good. Let me say two things. The first is I have to introduce a posterior for you, and then I have to give you your mission. Oh, yeah. That's as much as I can do. Okay, good. So, and that'll let me name check MCMC, which is something you're going to do in a minute. Okay, so you start with your prior. Your prior is the probability distribution for the parameters given your fundamental assumptions. And if you now update your beliefs, so how do I update my beliefs? These are, if you're a subjective Bayesian, which I am, this is supposed to represent your beliefs about these parameters before you started, which could be, you know, if you're doing LSST, it could be the things we've learned from WMAP and Planck. Now we're doing LSST. So then I take the LSST marginalized likelihood that you deliver to me. That's P of y given theta and I. That's the likelihood function. I multiply my prior beliefs by the likelihood. I renormalize it by something, which I'm going to talk about in a second. I renormalize it, and that renormalized object is the probability for the parameters given y and I. So I started with the probability of the parameters just given my assumptions, and I ended with the probability for the parameters given my data and my assumptions. See, we're now conditioned on the data because we observed the data. And various things to say here, but the most important thing to say is the updating of your beliefs is multiplicative. You take your prior, you multiply by the likelihood, and now you have your new beliefs. But then the next thing to say is this thing has units of per theta, this has units of per data, and this has units of per theta. So we had to change units. You see we changed units here? That means this thing has units. Z has units. Z is sometimes called the evidence, which is a terrible name that no one should ever use. And Z is usually very hard to compute. And that problem, that Z is hard to compute, that's what leads to MCMC. Markov chain Monte Carlo. The reason we do Markov chain Monte Carlo is it's a way to do integrals in these problems without ever having to know Z. So that is what you're about to learn in the next session. And now I have one last comment for you, and then I'm done. And that is the current design for the LSST pipelines is that LSST will produce posterior information, not likelihood information. If LSST goes down that path, it will have destroyed its legacy. Because if I'm going to use the LSST data, I need likelihoods. Your job is to ensure over the next decade and a half that LSST changes from thinking of producing posterior information to producing likelihood information, which is what we need. I'm done. Don't clap, it's a class.
Thank you, David. We have some time now for questions. I'll actually ask the first one. You mentioned a few times executable likelihood function.
Oh, good, yeah.
Can you define that term?
Yeah, good. I said executable. So one of the problems with these problems in general is when these spaces get very large. If your parameter space is very large, or if your nuisance parameter space is very large, or if your data space is very large, or if the relationship between your parameters and your data is complex, and by the way, all of those things are true for LSST, then it's hard to write down the likelihood function in a form that is computationally tractable. It's very easy to get into a state where a likelihood function call requires reading in the entire catalog and doing something crazy with all the different sources. So, if you have a trillion object catalog, doing this, computing your likelihood function can easily have a trillion squared operation inside it, which you'll never be able to execute. So there is one of the big things that's going to be a big challenge for your generation doing inference in cosmology is how to make approximations that allow you to either compute a likelihood function or avoid the likelihood function. And there's a lot of research going on that in various different fields, including in astrophysics. And some of the people who will be talking to you this week are experts at that. Is Foreman Mackey talking to the crew? Because Foreman Mackey is an expert in thinking about what you do if you can't write down an executable likelihood function. So one of the issues that I haven't talked about at all here is that, of course, what you really need to do is implement all this on a computer, and when is it implementable and when isn't it? In a lot of cases, it's not implementable. And a big part of what we do in my group is find approximations to make executable approximations to what we'd actually like to write down.
Other questions?
I probably got this. Well, the question is it the better way, the best way, or it looks like the only time where it's useful to use Bayes is when you have nuisance parameters? What if you don't?
Good. My view is that your job if you're producing, in any sense, producing data. So if you're either taking data or you're manipulating data and producing value-added data or whatever, if you're producing something that you want other people to use, you only have to produce a likelihood function. Therefore, you only use Bayes if you need to integrate out nuisance parameters. Otherwise, you don't need to have any priors. They're unnecessary additional assumptions you're bringing in that you don't need to bring in. You only need them to do integrals. In fact, in general, I would say an even stronger thing, which is that these probability distributions, like P of alpha given I and P of theta given I, these are measures for doing integrals. That's what they are. Like, they are part of measure theory. They're things for doing integrals. So if you're not doing integrals, you don't need them. If you're just optimizing, say you just want best fit parameters, you don't need this. You can just optimize your likelihood function. Why take on the additional assumptions if all you're doing is optimizing? You only need these functions for doing integrals. So fundamentally, it has to do with whether you need to do integrals. So if you're trying to make expectation values, like maybe you're trying to decide, should I use this model or should I use that model, and it depends on some integrals you have to do, well, then you're going to have priors because you're going to have to do those integrals. But if you don't have to do any integrals, don't bring the priors. You don't need them. And your users will only do the opposite of thank you if you multiply by the prior.
But then doesn't that mean that your user has to then run the thing? It's like if your goal is, oh, I'm going to
Good.
fit all of these galaxies or something like this, and I have a large multidimensional model. Like my job as a scientist is not to come up with the informative priors and just say, well, here's a likelihood function. Now you go run the supercomputer cluster code.
Yes, this is a big problem that everyone's facing right now. Is like whose responsibility is it to do the computing? So sometimes there's remarkable approximations. So the Gaia catalog. I don't know if people have looked at Gaia catalog, but I have a little paper on the archive also, which is called like a likelihood function for the Gaia catalog. It turns out the Gaia catalog is constructed so that if you use its mean values and its errors as parameters of a likelihood function, it's an approximation to the likelihood function. Meaning it's usually possible to release catalog information that gives you people a tractable approximation to the likelihood function. But fundamentally, if people want to combine data, use your data for another inference. Basically, if you're publishing data, you probably want people to use it in inferences. If you want people to use it for inferences, you either have to make it possible for them to execute your likelihood function, or you have to give them some approximation to the likelihood function. You really don't have any other choice. Otherwise, people can't use it responsibly. So that is an open question. And one of the reasons that LSST is leaning towards these posterior outputs is because people know how to make posterior outputs. They don't know so much how to release an executable likelihood function. But we are going to need to face this problem somehow in astronomy. That is the future of astronomy. Can I take one more?
So this came up a few times towards the end that you talk a lot about approximating likelihoods. I feel like a lot of the times what people do is like sort of wave their hands and say Gaussian in the residuals.
Yeah.
What can we do to go beyond that?
Good. In general, it's going to be generally the case that, like, for instance, when we use the Gaia data, the Gaia likelihood function is actually very close to Gaussian because the data are so high signal to noise, but it's not exactly Gaussian. But the thing that they released permits a Gaussian approximation to the likelihood function. So now imagine there was significant non-Gaussianity in that likelihood function. What would you do? And there aren't that many suggestions in the literature right now. One set of suggestions is what's done in large-scale structure. In large-scale structure, what's done is the full data analysis pipeline is simulated with numerical simulations of the large-scale structure, and the data is taken through the pipeline, and then they compare what comes out of the pipelines at the end. Because they can't actually compute a likelihood function for the data, so they just run the theory through the same pipelines as the data and compare the two at the end of the day. Actually, often with a Gaussian approximation, but whatever. People are looking at doing expansions. So you release the variance of your likelihood function, and then you release the skewness of your likelihood function and go on to higher moments. Mm-hmm. So people are looking at that, but it doesn't look very tractable for any kind of big data object. And then there are truly likelihood-free methods that are provably correct if your Gaussian isn't Gaussian, but it tends to involve a huge amount of computation of a different kind. And as I said, one of the experts in the world is Dan Foreman-Mackey, who will be talking to you later. Fundamentally, there's no well-defined program for how you make an approximation to a likelihood function. It's an art still, in the same way that making physical approximations is an art. And in fact, one of my themes is your data analysis involves just as much like theory and thought and analysis as the physical models that you're testing. They're both challenging theoretical entities.